Okay, so we recall we had a D flip-flop, and the D stood for data. And this was a piece of hardware that can remember one bit, either 0 or 1. So we had 2 inputs, and we had 1 output. And the way it worked was, I think if we put a 0 on the wire that opens it up for input, the other thing we can put here is we could put a 1 or a 0. Let's say we put a 1 here and a 0 here. That would allow this 1 to flow into this flip-flop, and the 1 would flow out. And then if we set this to a 1, that means we kind of locked it at that value. So then if we started changing this to 0 or 1, it wouldn't matter. It wouldn't affect that 1. That 1 would stay 1 until we reset it later on. And this is used for computer memory. We can store a number, which is really going to be a collection of zeros and ones, by opening up the gate, letting the number we want to set flow through, and then closing the gate. If we took a collection of these, collection of D flip-flops, it is referred to as a register. So if we had a series of D flip-flops, and we'll keep it simple, I'll say 4 of them for now. A series of D flip-flops. I'll put the input wires maybe on top, so this would be the open wire. And I'll change the color so we can kind of keep track of this. We have an open line, and then input values. And then we have output values. So all I've really done was kind of rotated them. Okay. So now I can set this to 0. That would allow the inputs to flow in by setting this to 0. And then if I set this to 1, it locks the whole set of them. So really nothing new here. We're just treating them as a set now. And we open and close them as a set. So this would be considered a 4-bit register. So we're grouping D flip-flops together, and then the open and close input gets grouped together into 1 wire. Okay, and then this will stay whatever number we want it to be for 1. So suppose we had a 4-bit register that had some values in it. It's currently equal to something. And let's just throw a question out. Suppose we wanted to create a piece of electronic equipment that said if all 4 of these are 0, then this one output should be 0. If all 4 of them are 0. If any one of these is not 0, then there should be a 1. So how could we do that? An AND? If they're all 0, the output should be 0. So we could just OR them together.
Oh, yeah.
Right? So, and remember from the electronics, we can make a multi-input OR gate. And we could just go like this. So if any one of these was a 1, this is going to be a 1. If they're all zeros, this will come out 0. Okay. Okay, so we'll use that in a second. This could be used, when could this be used in the real world? Suppose we had a particular register where a 0 here means there's no action to be taken, but if some number gets put in here, maybe these numbers, 1 up to 15 is what a 4-bit register can hold. 0 to 15, but let's say 0 means there's no problem, but if some number 1 through 15 showed up, we'll consider those problem 1, problem 2. And this line will come on, which means we have to handle a problem. And if this line is off, there's no problem to handle. So it could be used for something like that, right? Okay. Now suppose we wanted to have, let's have a new question. Suppose we had 2, I'll make these, because the wiring's gonna get a little complicated, I'm gonna make this real simple. I'm gonna say, if we have two 2-bit registers, this is register A, so there's only 2 bits to it. It's not very realistic in the real world to have a 2-bit register. And B, register B, which also has 2 bits. And then suppose we had another register, I'm gonna call this an interrupt register. Call it IR. Even though sometimes that's the initials for the instruction register. And suppose we had a question that goes like this. This register could have values 0, 1, 2, or 3, right? Actually, all 3 of these registers can go as high as 0, 1, 2, or 3. So suppose we had a value like 2 in A and 3 in B, and then let's say we had 2 also in the instruction register. Could we come up with some hardware that says if this register matches exactly, bit for bit, matches either this register or this register, then one of the 2 output lines, we'll have an output line for register A and an output line for register B. And that if this register matches this one exactly, then the line will be turned on. Otherwise, the line will be turned off. So we'll have 2 outputs. We'll have the one for A and the one for B. And if this register exactly matches this register, this will be a 1. This will come out a 1. And if there's any mismatch, then it'll come out a 0. And the same thing's true for the B register. So how can we do that? How can we decide if this register matches this register exactly? We'd have to check bit for bit that the bits match. So how can we say, does this bit and this bit match exactly? What could we say?
Would this be an AND gate then?
That, okay, so if they're both 1s, so we could do this. We could say, if they're both 1s, if this is a 1 and this is a 1, then that'll be a 1. They could also match by being both 0s, right? So if they're both 0s, how can we check are they both 0s? Well, we could take an AND gate. Well, actually, there's a NAND gate, but we'll leave it. We'll keep it simple, and then these little O's mean inverters. Flip the value around. We could say if this one is a 0 and this one, just connect to that line. So this is basically saying if they're both 1, and this is saying if they're both 0. Now, if either one of those is true, we're happy, right? So how can we say if either one is true? We run these into an OR gate. Now, this bit will be on if these match, either both 0 or both 1. That bit will be on. Okay, so can we connect it to the end here? Well, we want to make sure that the other bits match too. So our goal is to say if all of these bits match all of these bits exactly, we want this line to be on. Otherwise, we want that line to be off. So we could just repeat this thing again, right? Yeah, it's going to start getting crowded. This one, like just with 2 bits, you see it gets a little crowded. But basically, I'll do this. Goes into an OR gate, so if either they're both 1s or both 0s, that'll turn on. So we're doing this, and we're doing this, and that. Right? They're both the same. Okay. Now this will be turned on if the low order bits match. This will be turned on if the high order bits match. We want this to be turned on if they all match. They all must match. So what?
Now this would be an AND gate.
Yeah, so since they all have to be true, not just one of them, we'd run this into a big AND gate. So this would go in here, and this would go in here. And that should do it, right? So this hardware is checking that this register exactly matches this register. We can now copy, it'll just be messy, we could copy the same exact logic for this and this, right? So it's basically, the way this problem would scale to a bigger number was, we could make these registers larger. It's just going to be a big sloppy picture, but we're going to keep repeating the same logic over and over. And we don't have to have 2, we can have 16 or 32 or 64, but in the end we're going to have this big chunk of logic, and we'll have one output line for every one of the registers. If we did more across the top, we just have more output lines. So the way the question works was, there's one particular register and then a group of random registers, and we're asking, does this one match any one of these exactly? And if so, that line, that output line representing one for each register, will be turned on. Okay. Okay, so now suppose, so this is a new piece of electronic, and like I say, we could do the same thing for B. Now suppose, and it's customary to have the inputs on the left and the outputs on the right, but sometimes people have the inputs on the top and the outputs on the bottom. So suppose we have a new piece of electronic equipment that takes in as input 2 input lines, and this is really the output of the one we just did. So the 2 input lines come in, and let's say we have bigger registers. Let's say, in the real world they'll be much bigger, but I'll just make it like 4, I'll make it a register of 4 bits now. And another register. This is a different register from the question before. The question before was kind of like over here. And we put something in the, what we're calling the interrupt register. If it matched A, this line would turn on. If it matched B, this line would turn on. If it didn't match any register, no lines would be turned on. Okay, so now we have, we'll call this maybe A prime and B prime. This is a different register. Now it has 4 bits to it. And we have a new goal here. Our new goal is to have, we'll have one final register, same size as the primes. And our goal is this. So these could have numbers in them, like 0, 1, 0, 0, which is 4, and 1, 1, 0, 0, which is 12. Right, they could have any number we want. They could have any number the operating system set them to. But here's our goal. We want to come up with a piece of hardware that if this line is turned on, and we'll actually say we promise that at most only one of these lines will be turned on. They can't both be on. So the question now is, if this line is turned on, we want this entire register, which is, I just randomly said 0, 1, 0, 0, we want that to show up here. This is going to be like our output. We would like this to be 0, 1, 0, 0. If that's what the contents of this is and this line is turned on, then I want this to be copied here. If this line is on, then I want this content to be copied here. So the line that's on will determine which register gets copied over to here. So how can we do that? So we might want to copy 0, 1, 0, 0 to here, or we might want to copy 1, 1, 0, 0 to here. Or we might not want to copy anything. Maybe none of these lines will be on, and therefore this should be all zeros, if that was the case. So how can we do that electronically? How can we say, this line on means copy this stuff into here? Or, so I'm kind of like giving it away. Basically it's all ands and or gates. Yeah. Or if this line is on, then this has to be copied over. So there's going to be some ors in this. So basically, we could take this bit and this line, or this bit and this line. This line being on means we want these bits. This line being off means this thing should contribute zeros. So if we put on top of here, if we put OR gates here, so these are going to collect a bunch of stuff and then OR them together. And we want this number if and only if this line is on. Otherwise, we want to contribute a 0. So, if this line is on, this will feed a bunch of AND gates. This line should feed a bunch of AND gates. Which, I'm trying to think what's the simplest way to draw this. This line will feed a bunch of AND gates. And these outputs will go into the AND gates. Okay, so if this line is on, this line right here, if this is on, then these outputs should be this register, right? If this is on, then this being a 0 means this came out 0. This being a 0 and this 1, this came out a 0. 0, 0. This 1 and this 1 came out a 1. And this 0 and this 1 came out a 0. So basically, it would just copy the value of the register over. Okay? We did the same thing twice, and we did the same thing for this one. Let me draw these over here to make some room. Say this line will feed. And these will go in here, 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 and here. Same concept. And now, if I take the low order bits, I take this low order bit and run it into an OR, and this low order bit and run that into the same OR, and do that, now the picture will get a little sloppy. Maybe not too bad. This one goes into the third one, the third one goes into the third OR, this one goes into here, and this one goes into here. So now, if this line is on, let's say this line is on, and this line is off, what will happen? We will have, this line being off is basically going to 0 out all of these. Right? There's no two ways about it. This is going to be 0, 0, 0, 0. This one, this line being on, basically these bits will get copied out of here. So this will be 1, 1, 0, 0. They all get ORed together in the end, which means we have 1, 1, 0, 0 here. Now the only goofy thing would be, well, okay, so let's cover the case where they were zeroed out. If all the input lines were zeroed out. That would 0 out all the AND gates, and that would get, all those zeros would get ORed together and we'd have zeros, right? So if the lines are all zeros, the output's gonna be 0. Now the only weird thing, this is the thing we don't want to have happen, is if more than one line is on. Remember now, we can expand this. This doesn't have to be 2 lines. We can make this 32 or 64 lines. This is just to get the concept across. If both lines are on, what would happen? Well, in this case, there's nothing interesting would happen. Let me change this. Let me make it like this, just to make it an interesting example. What would happen is, this would be 0, 1, 0, 1, and this would be 1, 1, 0, 0. And then when we OR them together, we would actually get this, right? So, if we wanted to use a piece of hardware like this, that said, I may turn on one of these lines, or I may turn on none of them, we'd have to kind of have a promise. We'd have to know that at most one line would be on. If that's the case, then I can steer which one of these registers gets copied here. Okay. Okay, so now another piece of hardware that we could use, and we'll just start to glue these together shortly. Suppose we had a piece of hardware that did the following. We have, so our output is going to be another register, and let's say we'll make it 4 bits long. That's our output. And let's say our hardware, our arithmetic logic unit, or anything, our memory system, if it detects not a software issue, but a hardware issue. So like, let's say for example, you're running some software that says A equals B plus C, right? Do this in Java or C++. And all of a sudden, these are 32-bit registers each, and the value of these 2 numbers added together can't fit in 32 bits. You need 33 bits. You're going to have, I don't know if you've ever hit an arithmetic overflow exception. Okay, so basically, the compiler couldn't tell at compile time that you were going to try to stuff a number into A that won't fit. But as it was running, it figured it out. So this is going to be a runtime error. Yeah, right, the compiler couldn't know. Yeah. Even if it knew what B was and C was, B and C could change, and it can't. At compile time, the compiler can't figure out what you're going to change it to. So eventually, this line could run, and you're trying to stuff a number that can't fit into A. The hardware has to say, I can't go any further. Somehow has to signal that. So this would be what might be considered a hardware exception. So an exception is, you can have software exceptions or hardware exceptions. So a hardware exception is something with our electronics can't handle what the software is trying to do. So the hardware has to signal the operating system, I can't go any further, let's stop this program. So suppose the hardware has wires coming out of it. So this wire might turn on if there is a mathematical overflow error. And another wire might mean underflow. Another wire might mean you try to divide by 0, right? Like if you ever did A equals B divided by C, and the compiler can't figure out that C is going to be equal to 0 at the time. At runtime, you're going to have a divide by 0. So we could have, out of our hardware, different wires could come out, and that wire will turn on if the hardware detects this issue. So we'd have to wire up the ALU to say, if 2 numbers are added together and the result can't fit in the result register, turn this line on. If someone's trying to divide by 0, turn this line on, right? So we're just going to turn power on whenever we detect something's wrong. What we'd like to be able to do, if this is our interrupt register, what we'd like to do, if, let's say this line turns on, maybe we'd like to store a number, maybe as we designed our chip, we decided mathematical overflows are a 3. Wait, 0, 0, 1, 1. And maybe a divide by 0 is an 8. So if we detect the divide by 0, it'd be nice if we could put an 8 in here. So the hardware is basically just sending power out, but we kind of like to collect it all together into a register. So, oh, if I see an 8, I'm just making this up, but 8 means divide by 0, 3 means, you know,
Yeah.
different numbers mean different things. And let's use the convention that all zeros means nothing's wrong. Everything's fine. So we, like we did before, we can run this through a big OR. And if this output is 0, everything's fine. If this output is not 0, something's wrong, right? And then if something's wrong, we should read this number to figure out what is wrong, and then do something about that. Okay, so that's why we wanted to do that thing before. So now, how can we, let's say this line being on means let's put a 3 in this ring. I'm just making up numbers, but let's say put a 3 in there, and for this one we'll put an 8. And I think it'll start getting complicated if I add a third one. But we're just, as the chip designer, we're deciding, let's see, if it doesn't get complicated, we can add a new one. Okay, so if the ALU sends electricity out of here, the ALU detected, let's say 3 means overflow. And 8 means divide 0. So if electricity comes out of here, we detected an overflow. If electricity comes out of here, we've detected a divide by 0. How can we store if electricity comes out of here, I want to put a 3 here. If electricity comes out of here, I want to put an 8 here. And obviously we can go, if it's a 4-bit register, we can put numbers between 1 and 15 for problems. And across the board, zeros means no problem. So how can this line put in, how can we have this turn, this line being on turns this register into 0, 0, 1, 1. How could, this power comes on, that's going to happen. We can obviously, zeros are ground, right? You know, no electricity. And we can take ground, so this is a 0. And we can take ground and run it through an inverter, and that's a 1. This is just like if, let's consider it an outside source. This is zeros coming in from the outside world, these are 1s coming in from the outside world. So we know this will always be 0 and this will always be 1. Okay, so we use that as a source. Now it's just, what, AND gates? And we're just saying, if this line is on, kind of the same principle we just did before. We will take AND of a 1, then this, and now we're going to do it for everything else. So we're going to need ORs again. Okay, so this gets ended with a 1. This one also gets ended with this line. That runs into this OR gate. And then this line gets ended with the zeros. Take this power line, run it into here and here, along with the 2 zeros. Okay, so now what's coming out of here, what's coming out of these is basically the number 3. Right, the 0, 0, 1, 1, because I've wired up 1s with this line. So that would send 1s out of here and zeros out of here. Now, hopefully it shouldn't get too messy. What about the case where we want to put an 8 in this register if this line is on? Same, pretty much the same idea, right?
Just flip them, right? Flip the, I mean, where the ones get fed into the AND gates. We'll do that.
Yeah, but I guess we could, this might not be the smartest way to do it. We could probably, after we're done drawing this, we could probably simplify it, but we could just do this. Do another, do a different color. Let me, yeah, I'll do this purple color. So this wire goes into each one of these. And then we need either zeros or ones. So we want, if this line is on, we want an 8 to flow out. So an 8 would be this thing, a 1 goes into there, and zeros go into here. So we'll just connect to the 0 line and go 1, 2, 3. So if this line turns on, an 8's going to come out of here. If this line turns on, a 3's going to come out of here. And if they both turn on, then we're going to have some combination problem. So hopefully our program only hits one problem at a time.
Yeah.
Okay, so then we feed these results into this big OR gate. So now, if the 3, so if let's say the only two interrupts right now are 3, the number 3 and 8. If this line turns on, this register will take on the value of 3, as soon as the electricity flows through. If this line turns on, this register will take on the value of 8, as soon as all the electricity flows through. If for some reason both problems hit, divide by 0 and overflow at the same time, we got a really screwed up program. But if that happens, then we'd end up with some kind of, we'd end up with what, this, right? 8, 0, 1, 1. But assuming that's not the case, if we design our hardware so that at most only one of these lines turn on, then we could assign this register to some number. We could just print out a chart what the numbers mean. Then we could take the output of this. If it's zeros, nothing's wrong. If it's not zeros, that means some number higher than 0 is in here, and we need to handle that. Okay. And then the last piece of hardware I think we'll need, and then we just could put these pieces together, is a piece of hardware. This is going to be a little higher level, now that we have the stuff we've already talked about. Suppose we had a table of registers. So let's say we had, 4-bit registers, and make it a bigger number, like 16 bits. And we could have up to, since we have 4 bits, we have 2 to the 4. Equals 16 such columns, like this. Okay. And suppose we had, so what this is going to now represent is, suppose we had 16 different possible interrupts. It's the 16 different things that could go wrong. And each of the 16, we have some software routine that if this interrupt happens, like let's say, you know, if you divide by 0, the operating system needs to kick off some routine that it can't let your program continue. It has to say something like, you have tried to divide by 0, I'm kicking your program out and removing you from the operating system. Any files you have open at the time, it's going to close so you don't leave a mess behind you. Yeah. There's going to be a whole bunch of operating system software that will run if this interrupt hits. So we create a table that has really 2 columns. It's a column of 4-bit registers and then a column of, let's say, 16-bit registers. And as input, we have the interrupt register. the problem that went wrong. So if we OR this whole thing together, and it turns out that power comes out, that means something's wrong. We now want to be able to say, I want to compare the number that's in here. A 3 would mean, like we made up, a 3 would mean an interrupt happened, an overflow happened, an 8 would mean divide by 0, whatever it is. Does this register, bit for bit, match any one of these? We'd like to know the answer to that. If so, a power line will be turned on. So we can wire this into this whole column, just like we had the example with the A and the B, now make it 16. So we're wiring one register into 16 and we're asking, is there an exact match, bit for bit exact match? If so, send power out. So this, you could actually, maybe I should have broke this up. It's generally drawn together, but maybe I should have broke it up like this. Same color. So this will be 16 bits. And these are totally different bits. These are actually going to be an address in the operating system where the routine starts. So what we'd like to do is we'd like to say if somebody puts a number in the instruction register that's other than 0, a power line will turn on, which will then cause us to kick off that piece of hardware we drew before that says, do these 4 bits match any of these 4 bits exactly? If so, remember these each had a power line coming out of them. Last time we had 2, but now we have 16 power line coming out. And then the question is, what I'd like to do is take these 16 bits and put them into some 16-bit register. I would like whatever number is here to flow into here if this power line turns on. And that's what we just did before, but now we're just multiplying it by 16. So we could take all of these run into a OR gates all over the place. Blah, 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 and then an OR gate here. And all this stuff, there's a whole big cloud of hardware here that will take these 16 bits and copy them here if this line is on. The next 16 bits, if this line is on, will get copied here, and so on. So what this ends up being, this 2-column table, depending on what it's used for, has different names, but a pretty popular name in the operating systems world is called a translation. So you could see its translation comes in because, like, a translator is someone who speaks English and Chinese. You say English, they say the Chinese. This is, you give me one number, I'll give you the corresponding matching number. So there's a translation going on. They call it Lookaside. Not exactly sure what this means. You find a match here, and then you look over to the side and find the match. I don't know where that came from. Translation Lookaside Buffer. So, and a buffer is a place where you can temporarily hold stuff. So what we could do, if let's say this piece of hardware we're creating, this translation Lookaside buffer, had only 16 slots in it, but maybe we had 50 interrupts, but maybe as a program's running, there's only like 10 interrupts that could possibly hit this one, we could load and unload entries in this table, and that way we don't need to have a piece of hardware big enough for every possible interrupt. So we can consider this a buffer that we could write lines of data to it and then come back, and since these are actually D flip-flops, we can change them if we wanted to. So now what we have is whatever is here gets copied to here if that particular interrupt happens. So if interrupt 3 happens, if 0011 gets written to the interrupt register, that means problem 0011 has happened. These bits will all be ORed together, and if any of them is on, that means we have a problem. If one of them is on, that electricity will come in and cause us to check, do these 4 bits match any one of these 4 bits exactly? If so, that'll send power into this table, which will then take whatever address is here and copy it to here. So in the speed of electricity, not the speed of we could have written software to do all this too, right? We could have had an array of 16 bits, an array here, and then we could say if these 4 bits match the first one, then copy this to here. Else, if then these 4 bits match the second one, copy here. But that'll end up taking like 16 instructions just to get the address here. We need this right away. So we'd rather software, you could do anything in software, right? Bill Gates says you can do anything with software. But it would take time. We need this done quickly, so we're coming up with a piece of hardware that could do it. So really what'll happen is we'll put, anytime we apply any number here that's not 4 zeros, just at the speed the electricity flows, they'll be ORed together. The bit being turned on will cause a hardware search of these 4 bits against any set of 4 bits here. If a match happens, one of these lines will be turned on. If one of these lines is turned on, then these 16 bits, the 16 bits that correspond to the interrupt number, will get copied to here. And this ends up being the address of the software that's going to handle that interrupt. And then all of a sudden, when your program is running, and we'll talk about processors a little bit later, a processor will take a program and take an instruction and say, here's the instruction I'm currently running, and it has a pointer to the very next instruction. When the current instruction finishes, it goes to the pointer to the next instruction, loads that one, and runs it. What we're now going to do is we're going to load this instruction, which is the beginning of the operating system routine, which will clear away your program because your program screwed up and needs to be cleared out. So this is how we can take the instruction of the operating system software that handles the error that you hit, the exception that you hit, and have that start running and have your program stop running. And this would be a lot quicker than software going through a table looking for a match. So we needed a piece of hardware to do this. This was for speed reasons. And obviously, we could do anything we can do with software, but it would be a lot better if hardware was used. So for example, if you have, if you're moving your mouse around on a computer, we could have had software that says, if the mouse is currently over this link, then, like sometimes when you put your mouse over a link at the bottom of the screen, it lights up what would happen if you click it, but you haven't clicked it yet. So we could say, as you're moving the mouse around, actually events are happening. We could have software that's constantly tracking where you are, but that could take a lot of time. It might be better to just have a hardware register that throws numbers in, and then based on what number gets put in, determines what event is happening. And if you put your mouse over a link, maybe one number gets put into a register, and then if you click on it, a different number gets put in, and if a different number means you have to handle something, it'll handle it. So a little bit of a trade-off when you want to use software and when you want to use hardware. But something where a lot of speed is involved, it's sometimes better to come up with a hardware solution. It's painful to design it once and build it, but then once it's built, it's very easy to just copy over and over. So, you have any questions about this? Okay. So this type of hardware, it's not necessarily used just for operating systems. It could be used anytime we need it. But we just want to get comfortable with the idea that we can have a register, which is a collection of D flip-flops, and then have an array of registers, and we can wire them together so that we can search this set of bits looking for a match, and it'll be done instantly. Speed of electricity rather than software going through the whole array looking for a match.